The visualization opens with a slowly rotating Earth, revealing a living ocean in constant motion. Streams of light trace the pathways of global ocean currents, wrapping the planet in an intricate and dynamic system that drives Earth's climate and redistributes heat, salt, and energy across the seas. This is Perpetual Ocean 2, a three-dimensional visualization of ocean circulation created using NASA's Estimating the Circulation and Climate of the Ocean model, known as ECCO. Developed in collaboration between NASA's Jet Propulsion Laboratory, MIT, and the University of Texas at Austin, the ECCO model blends satellite observations, drifting buoys, and in-situ measurements to capture the true movement of the world's oceans. The data shown here comes from ECCO 2, covering the years from 2021 to 2023. In this beauty version, color choices emphasize elegance and clarity. Ocean flows from the surface down to 600 meters appear in white, while deeper currents transition through soft tones of blue and cyan, revealing the hidden motion beneath the surface. Millions of virtual particles are released into the ocean, each leaving behind a glowing trail that reveals both speed and direction. Particles near the surface trace 3 days of movement, while deeper particles reveal 6 days of flow, exposing the powerful currents compressed into narrow bands along the western edges of ocean basins. These are known as western boundary currents. The journey begins in the Pacific Ocean, along the western edge near Asia and Australia. The camera zooms toward Japan, where the Kuroshio Current races northward along the coast. Here, the current forms large, looping meanders that can remain locked in place for months. The Kuroshio carries warm waters, typically between 20 and 25 degrees Celsius, with salinity averaging around 34.5, varying with the seasons as it transports tropical heat toward higher latitudes. Pulling back, the view shifts westward into the Indian Ocean, a basin marked by striking contrasts in salinity. The western Indian Ocean is highly saline, enriched by dense waters flowing from marginal seas, such as the Persian Gulf and the Red Sea. To the east, fresher waters dominate, influenced by freshwater input from the Indian subcontinent. Flowing between these regions, the Indonesian throughflow carries relatively fresh water from the Pacific, linking the two great oceans. The camera then moves south toward the tip of Africa, where the Indian and Atlantic Oceans meet. Here flows the Agulhas Current, one of the most powerful and stable western boundary currents on Earth. Hugging the steep and narrow continental shelf along southeastern Africa, the Agulhas Current remains tightly constrained, avoiding the broad meanders seen in other currents. As it reaches the southern tip of the continent, the current overshoots into the South Atlantic before sharply turning back toward the Indian Ocean. At this point of retroflexion, massive warm and salty rings break away from the main flow. These Agulhas rings, with temperatures between 20 and 25 degrees Celsius and salinity near 35.5, drift into the South Atlantic Ocean. Some of these swirling vortices persist for more than 2 years, carrying heat and salt thousands of kilometers and playing a vital role in global ocean circulation. The focus then shifts to the western boundary of the Atlantic Ocean, where the Gulf Stream emerges from the Florida Straits. One of the fastest currents on the planet, the Gulf Stream reaches surface speeds of up to 2.5 meters per second as it surges northward along the eastern coast of North America. Near Cape Hatteras, the current peels away from the coastline, forming large meanders that spawn immense cold core and warm core eddies, some stretching up to 1,000 kilometers across. A closer look reveals warm surface waters, glowing white, flowing poleward with temperatures exceeding 25 degrees Celsius. Beneath the surface, deeper blue particle trails expose a southward return flow at depths greater than 500 meters, transporting colder polar waters back toward the tropics. This layered circulation highlights the three-dimensional nature of the ocean, where surface and deep currents move in opposite directions. In the Gulf of Mexico, Looping currents form long-lived vortices that draw warm, highly saline Caribbean waters into the basin, storing heat and influencing regional climate. As the camera pulls back once more, the salinity patterns reveal a final contrast. The Atlantic Ocean, in general, is far saltier than the Pacific.